This study is conducted purposely to identify the one-week change of COVID-19 cases in the whole world. Many factors that have been taken into account by the specialists, such as the rate of recovered cases, the rate of dead cases, the number of new recovered cases, the number of new dead cases, and the number of new COVID-19 cases. This study is really important for the specialists to identify the trend of COVID-19 cases in each country, so that they will know which country is more symptomatic with this type of virus. Later, they can find ways on how to stop the virus from spreading to other countries widely.
Okay, now I will explain about demographic profile. As we can see that this table of demographic profile consists of 7 columns, which is the variable x1 until x5 and y, the level of each variable, the mean, the standard deviation, the minimum, the maximum, and the total of each variable. All of the data obtained was explained in histogram since all the type of variables is in numerical and all the level of measurement of the variables is scale. Therefore, it is easy for us to explain all the data in histogram compared to the other type of chart. The variable x5, which is the new cases, has the largest value of mean and standard deviation compared to the other variables of x.
Next, we'll proceed to the regression model of the original model. Look onto the table provided. Under the parameter estimate column, we've got the values for every coefficients for the full original regression model equation. The equation is y hat equals to 414.73693 minus 17.09692 x1 plus 22.35307 x2 plus 5.68305 x3 minus 64.32197 x4 plus 5.4214 x5. And each of the variables have their own specific meaning and description. So we start with y hat. Y hat stands for the number of 1 week changes of COVID-19 cases. For x1, the number of recovered over 100 cases. For x2, the number of death over 100 cases. For x3, the number of new recovered. x4, the number of new death cases. And lastly, for the x5 is the number of new cases.
I will be presenting the general model fitness for the first model. Okay, the first model is a good model because it is significant. If the p-value is lower than alpha 0.05, the p-value that we have is 0.001. Next, there are 3 significant predictor variables and 2 insignificant predictor variables, where the x1 and x2 is the insignificant predictor variable and the remaining is a significant predictor variable. Next, the R-square value is 0.9603, where we can conclude that 96.03% of the total variation in 1 week change of COVID cases is explained by the predictor variables, by all the predictor variables. Next, while the adjusted R-square value, 95.90% of total variation is explained by the model after considering the number of parameters p equals to 6 and the number of samples n equals to 187. Multicollinearity might exist because the root MSE, which is the standard error of the estimate, is too big, which is the value is 95, 92.595 and 76.
Linearity. As we can observe from this scatter plot matrix, we can say that there is a positive weak linear relationship between the number of new recovered cases x3 and the number of 1 week change of COVID-19 cases y. There is a positive weak linear relationship between the number of new deaths x4 and the number of 1 week change of COVID-19 cases y. There is also a positive weak linear relationship between the number of new cases x5 and the number of 1 week change of COVID-19 cases y. However, there is a no relationship between the number of recovered per 100 cases x1 and the number of 1 week change of COVID-19 cases y. And there is also no relationship between the number of deaths per 100 cases x2 and the number of 1 week change of COVID-19 cases y. Since there is a no relationship and there is a positive weak linear relationship, therefore, we need to do a transformation on this model.
Okay, the second assumption of model adequacy checking in multiple linear regression is the normality of the error curve. We can see from the Q plot of residuals for the number of one-week change, the error points are not normally distributed, since most of the points are distributed so far and not aligned on the 45-degree straight line. We can also see that there is a S-shaped curve that is shorter than normal tails. Therefore, this indicates less variance than expected.
Next, for the independence of error terms of original model. The W-Watson value obtained 2.027 is within the range of 1.5 and 2.5. Thus, we could assume that the error terms are independent and there are no serial correlation problems in the model.
Okay, for this graph, the plot against the predicted values is a non-constant variable as the variance of the residual is not constant across observations. It also graphically means that the spread of points around the regression line is variable.
I will explain about the multicollinearity. From the table above, we can see that there is a strong correlation exists between the variable new recover and the new cases. There is also a strong correlation between variable the new deaths and new cases and the variable new recover and the new cases. So there is a possibility that the multicollinearity will happen here. From this table, there is a multicollinearity problem in this dataset. This can be seen from the given output above that the collinearity statistic for variable the number of new cases has a value 11.152 in the variant inflation factor. Multicollinearity exists when the value of VIF is more than 10. Tolerance statistic for variable the number of new recover and the number of new deaths have a value 0.152 and 0.115 respectively. Even though the value of TOL is below 0.2, we cannot conclude that the multicollinearity exists because the value VIF for both variables is not above 10. From the diagram above, we can see that there is 8 leverage points exist as outlying cases with regard to the X value. So, we use SPSS to identify which observations are outliers. From this graph, there is no line or boundaries that exist in the graph. So, we use SPSS to get the value of DF. This is the SPSS output that we get. For checking the outlying Y, we observe values to the touch residual and get that observation 24, 38, 80, 133 and 174 have a value more than modulus 3. For outlying X, we use formula of head matrix leverage value and value that above 0.0642 are the outlying points of X. There are several observations that become the outlying points of X. To check the inflation cases, we use formulas Crookes distance and DF fits. For Crookes distance, value that above 0.0221 are the inflation points, while for DF fits, value that above 0.3582 are the inflation points. In conclusion, observation 24, 38, 80, 112, 133 and 172 are inflation points. Thus, this observation need to be removed.
Transformation of the model. Firstly, after removing the outliers, which are the influential cases in the first model, observation number 24, 38, 80, 112, 133 and 172, we need to remove the insignificant variable X from the first model. Secondly, independent variable X, which are the number of new recovered X3, the number of new deaths X4, and the number of new cases X5 need to be transformed to improve the linearity towards independent variables. Next, the number of new recovered X3 is being transformed to transform X3 by using formula transform X3 is equal to ln X3. The number of new deaths X4 is being transformed to transform X4 by using formula transform X4 is equal to ln X4, and also the number of new cases X5 is being transformed to transform X5 by using formula transform X5 is equal to ln X5. Next, this is because the scatter plot matrix obtained shows that there is a weak linear relationship the weak positive linear relationship only. Therefore, hence transformation is being done. There are also a need for transformation for Y. That is one week change of COVID-19 cases because the error terms are not normally distributed and the error variants are not equal in the first model. Hence, the number of 1 week change of COVID-19 cases Y is being transformed by using formula transform Y is equal to ln xy.
Alright, for the final model, we've got the another version of the regression model. The variables are labeled as transform Y, transform x3, transform x4, transform x5. For each transformation variables, we conduct the ln Y and ln X to make this final model. Therefore, the new equation is ln Y hat equals to 2.74 plus 0.142 ln X3 plus 0.105 ln X4 plus 0.716 ln X5. Ln Y hat is actually the natural log of number of 1 week changes of COVID-19 cases. For ln X3 is natural log of number of new recovered. For ln X4 is the natural log of number of new deaths. And lastly, the ln X5 stands for natural log of number of new cases.
Next is the general model fitness for the final model. We can see the final model is a good model because it is significant. The p-value given is 0.000. So, we can conclude that it is a good model. And all the predicted variables are significant because the p-value is less than alpha 0.05. The p-value for the third variable is 0.000 and the fourth variable 0.30 and the fifth variable is 0.000. From the model summary, we can also find out the R-square, adjusted R-square, and standard error of estimate. First, the R-square value is 0.942, so we can conclude that 94.2% of total variation in number 1 week change of COVID-19 cases is explained by all the predicted variables. Meanwhile, the adjusted R-square is 94% of total variation is explained by the model after considering the number of parameters p equals to 4 and the number of samples n equals to 181, while the remainder 6% is explained by random error. Lastly, no multicollinearity might exist in this final model because we can see the value of the standard error of estimate is too small.
Linearity after transformation. So this is the scatter plot matrix that has been obtained after the transformation has been done. It can be concluded that there is a positive strong linear relationship between the natural log of number of new recovered ln X3 and the natural log of number of 1 week change of COVID-19 cases ln Y. There is also a positive strong linear relationship between the natural log of number of new death cases ln X4 and natural log of number of 1 week change of COVID-19 cases ln Y. And also there is a positive strong linear relationship between the natural log of number of new cases ln X5 and the natural log of number of 1 week change of COVID-19 cases ln Y.
The normality of the error term in the final model. We can see from the QQ plot of residual for ln Y, the error terms are normally distributed since most of the points lies on the 45 degrees straight line. And we can confirm that by having the output plot SPSS, where the normal PP plot of ln Y also shows that the error terms are normally distributed because almost all points are aligned on the 45 degree straight lines.
Next, we proceed with the independence of error terms for final model. The W-Watson value obtained 1.972 is within the range of 1.5 and 2.5. Therefore, we could assume that the error terms are independent and no serial correlation problems in the model.
From this graph, the plot against the predictor values is a non-constant variable as the variance of the error term in residual variance is not constant across observations. It is also graphically means that the spread of points around the regression line are roughly not the same for all the data.
There is a strong correlation between the variable transforms x3 and transform x4. This is because the correlation coefficient of these two variables is more than 0.8. So, there is a possibility that multicollinearity will happen here. From the collinearity statistic table, we can see that there is no multicollinearity in this dataset after transformation has been made. This can be seen from the given output above that the value for variance inflation factor for each of the variables is less than 10. Value tolerance statistic for each of the variables also is more than 0.2. So we can conclude that the multicollinearity does not exist in this dataset, even though there is a strong correlation between the variables. There are 4 leverage points that exist as outlying cases with regard to the x value. We can see that observation number 17, 39, 105 and 168 are outlying points in this model. From the graph above, we can see that there are 4 observations exceed the threshold line. As we can see, observation 8, 39, 172 and 179 are the inflection points in this model. In conclusion, there are several outliers and leverage in this final model, even though transformation has been made.
So, in conclusion, due to decision in our group, we decided to improve the linearity for each variable by doing transformation. Transformation toward y into the formula ln y is also being done because there is non-normality the error terms and also unequal error variances. After those transformations had been connected once, we finally achieved our final mode where almost all the assumptions have been satisfied. Thank you.